Okay, this will be our last prep video for the semester, so we will be looking at section 6.1 and 6.2. Basically, we're looking at applications now. So we're going to cover these three, the Gini index, probability density function, and then producer and consumer surplus. This last third one we're going to do entirely during class, so I'll take that one off, and we'll just look at these first two. Okay, so let's start with the Gini index. The Gini index is actually based on something called the Lorentz curve. And this has to do with the Lorentz function, I guess, curve, of income distribution. So this application is all about determining if income is equally distributed among a population. So we're going to graph this Lorentz curve. And what the Lorentz curve does is it says, let's say, so this is going to be percent of income. And this is going to be percent of population. And this is called a cumulative graph. So what it means is, by the time we get out here, and we're all the way at 100%, and actually this one's done in decimal, so we're thinking percents, but really it's a proportion. So when we get out here to 1, that means we've taken into account all of the people who could earn income. And at that point, we should have accounted for all of the income. And down here at 0, when we've counted nobody, we should have counted none of the income. So then how do we get from here to here? Well, if everything's evenly distributed, then half the people should account for half the income. And a quarter of the people should account for a quarter of the income. And so this will be a straight line of slope 1, assuming that everything is evenly distributed. Everybody, and so remember, this is cumulative. So the bottom quarter has a quarter of the income, the bottom half has half the income, and by the time you get to everybody, that accounts for all the income. Well, clearly we know that this is not the case. We know that in our country. We talk about the top 1%. They're going to have a lot more of the income, and so so this is an ideal Lorentz curve. Right? I shouldn't say ideal. This is where you have perfectly equal distribution. In reality, curves look more like this, or maybe even at worst case, like this. And what that says is, here, a quarter of the people maybe only account for 10% of the income. And maybe here at half, it's not even much better. And then all of a sudden, you get to this top, and all of a sudden, one person, or a handful of people have everything, have all the income. So clearly, this is less evenly distributed than this one. So this is what a Lorentz curve of income distribution is about. You might be interested to know that most people think of, when we talk about the top 1%, that's pretty common to talk about these days, most people think, oh, that's people making $1 million or more. In reality, the top 1% starts at about $350,000. So what that suggests is, if you were to blow up this part of the graph, and just look here from, say, the 99th percentile up here to 100, this is going to be unevenly distributed as well. How do I say this? So there are going to be a lot of people in the $350,000 range, and then all of a sudden, and that's going to kind of slowly, gradually increase, and then all of a sudden, there are a few Bill Gates. So this is a Lorentz income distribution curve. So how do we use this? And this is where we look at the Gini index. What the Gini index says is, the farther away your real income distribution curve is, away from perfect equality, we can make a measure of that. So we want to know, essentially, how far away, let's take this bottom curve. We want to know how far away that is from here. Well, one thing to do is to simply add up that area. Right? The further the curve is away, the bigger the area is going to get. So how do I find that area? Well, we know that area between curves is just the integral over the area of interest, upper curve minus lower curve. So that's what we're going to do here. So the Gini index starts like this. 0 to 1, nobody, up to everybody. The top curve is going to be this equal distribution. The top curve is x. It's a line with slope of 1. Minus whatever the Lorentz curve is, dx. So let's see if that makes some sense. So worst case scenario, nobody has anything and one person has everything. So the max that this area can be is this triangle, right? Just the whole triangle there. So the maximum area we can get here would be a triangle. It's got a width, a base of 1 and a height of 1, so 1/2 base times the height, 1/2, 1 times 1 equals a half. Well, somebody decided that having the maximum be a half wasn't as useful as having the maximum be 1. And so this was just introduced just to make the numbers work out more nicely. So this part has to do with the area. That 2 in the front is just to kind of make the whole thing go from 0 to 1. So this is your Gini index. Okay, so that's a pretty easy thing to figure out. If we know the Lorentz curve, we just drop it in and do the integral. So let's look at, on page 390, number 90. Let's see if I have some, I'm just going to try and do it right here. So this one says, using data from the US Census Bureau, an economist produced the following Lorentz curves for the distribution of US income in 1962 and in 1972. And so this is what we have. So for, I'm going to try and write it up here. So for 1962, the curve was 3/10 x plus 7/10 x squared. And in 1972, one half x plus 1/2 x squared. Okay. So how do we go about finding the Gini index for these? What we're trying to answer is, has income distribution gotten more equal or less? So let's take a look. Let's do the one for 1962 first. So from 0 to 1, x minus, I'm going to open parentheses. Anytime you're going to subtract, go ahead and open the parentheses so that you make sure to distribute that negative. So I'm going to, I'm just going to change those to decimal because we can. So 0.3x plus 0.7 x cubed. You know what, maybe I didn't want to do that. Let's not do that. Okay, so this is just a polynomial. It's going to be pretty easy to work all that out. So let's go to here first. X minus 3/10 x would be 7/10 x minus 7/10 x squared. So all of that. I'm going to go ahead and pull the 7/10 out front. So I'll have 14/10, 1.4. And then I just get a very easy integral to do. So we're going to work through the integration. I'm not going to work out all the details. So 1/2 x squared minus 1/3 x cubed from 0 to 1. So in the end, we're going to get, when you run out all of those numbers, the answer turns out to be 0.233. So if 1 is the very worst it can be, that one seems, maybe okay. I'm not sure what is a good number and what is a bad number. I don't have a lot of experience, but I know that 1 is the worst, and we're not near there. So for 1962, we got 0.233. And if you do the same process for 1972, you get 0.167. Okay, so then what does that tell us? Remember, the closer the curve is, the smaller the area will be. So the smaller the Gini index will be. So smaller is good. That means closer to the ideal. So in this case, it suggests that there was more equal income distribution in 1972 than there was in 1962 in the US. Okay, so for the Gini index, you have your Lorentz curve. You just drop it into this formula, which I will give you. That's not something you need to memorize. And then just work through the numbers. Okay, so that's the Gini index. Now let's look at probability density functions. Give myself a little more space. Okay, so here we go. So probability density functions. if any of you have taken statistics, this is the same probability that we're talking about. I'm going to give you a little brief overview of probability for those of you who have not had it. Okay, so we know some things. We know that if we have a 100% chance of something happening, that means it's certain to happen. We do probabilities not in percentages, but in decimal. So the decimal equivalent of this, the probability would be equal to 1. We also know at some point we have a 0% chance of something happening, which means it's impossible. And again, in decimal would be 0. So what do we know? Can we be anywhere outside of this range? No. It's either certain, or it's impossible, or it's likely, very likely, unlikely, less likely. Those are the kind of phrases we use in here in the middle. So we know that probability must go from 0 to 1. And up here we would say likely, unlikely, just kind of filling in the rest of the scale. You know, equally likely. And those would just be numbers ranging from 0 going up to 1. Okay, so we can actually, we have different kinds of things we can think about. So like you could think about rolling a die, 6-sided, so there's 6 different things that can happen. So you can make a table and you can say, what are the different things that can happen? Well, I could get a 1, 2, 3, 4, 5, 6. How likely are those to happen? Well, if it's not a loaded die, right, if it's a fair die, each one of these will happen 1/6 of the time. And this is called a probability density function. The probability distribution, maybe that's a better way to say it. So this is a probability distribution. And I can write this for anything that's discrete. So I could roll dice, I could roll more than one die, I could look at the sum of the faces, I could look at the combination of faces, I can flip coins, I can flip coins multiple times, I can flip 2 coins at a time, you know, any sorts of things. You could, decks of cards are another real popular one. So this would be a probability distribution. And we can simply look up what's the probability of this happening and just look it up in the table. This is for what's called discrete. That means I can list every single thing that can happen. So I can't get a 1.1. I can only get a 1 or 2. So this is discrete. That brings us to something that's continuous. What would be something that you would measure that would be a continuous number? Well, that might be something like time, or height, or basically anything that you can measure. Yes, I know that your watch maybe only goes to the millisecond. Okay, so fine, you can't really measure finer than that, but in reality, we know that time you could measure down. If you had something good enough, a tool good enough, you could measure down to any amount of time you wanted. So this is time. A good example of continuous would be time. So when we're looking at this, we're not going to be able to list everything. So instead what we do is we draw a picture. And so this would be time on this axis, and maybe you have something that looks like this. This is a bell curve. You guys are probably familiar with that. Interesting thing about the bell curve, also called the normal distribution, is that this here in the middle, the mean, is the most likely thing to happen. So this is probability, is that what I want to write? I think we usually make this an X. I mean, often we refer to time, but usually when we're talking about these, we write it that way. So this is the probability. So clearly, the thing that is most likely to happen is this thing in the middle. The thing that's least likely to happen is over here. And that makes sense when we think about real life. If we look at heights of people, most people are in the middle, a few are very tall, a few are very short. And the normal distribution governs a huge number of things in our real world. It doesn't have to be a normal distribution, but there are some things that we need to know about this. So for one thing, so X is what's happening, P is the probability of that thing happening. Here we said that the biggest probability can be is 1. And so I miswrote this. Let me take this off. The probability is actually the area under the curve. So all of this area under here, if I were to add it all up, the biggest that area can be is 1, because we know we have a maximum of that. So a couple of things. We know that probabilities are always greater than 0. And we know when we integrate over the entire range, we should get exactly 1. Not less than 1, not more than 1, but exactly 1. So this is for all the way, however far it goes. So then the more interesting question, so this, like this, is a summary of what can happen. So this is sort of individual probabilities of things happening, but the total probability is going to be the area under the curve. What's most interesting is, what if you wanted to know the probability that it's between two numbers? Like, let's say, let me just write it out and then we'll do an example. So if I wanted to know what is the probability that x, the thing that can happen, is between two values, I'm just going to integrate from c to d of that probability density function. So that's what this is. This is a continuous probability density function, PDF for short. So this is not really probability, this is kind of a distribution of the probabilities. And so I'm just going to integrate that over the area, the interval of interest. Okay, so let's do an example. So we're going to look on page 401. Let me see, what can I erase? And so the reason that this is an example of using integrals is that here we're doing the area under the curve from A to B. And so that's our probability. So page 401. Number 26 says this. And so this is an excellent example of where this is interesting in the business world. The shelf life in years of a laser pointer battery, or anything else that has a shelf life, is a continuous random variable. That's some language I haven't introduced. It's basically saying x can take on any value, right? X can take on any value in years, and it's given this way. And I'm limiting the domain to x being greater than 0 because, of course, we know that something can't last a negative number of years. So here's the question. First one is, find the probability that a randomly selected laser, just someone you got off the shelf, has a shelf life 3 years or less. Okay. I'm not going to check out that this satisfies all the other things that we needed it to. We know it's greater than 0. We can see that. If x, no matter what x is, we can't get a negative number out of here. If I integrate over the entire domain, I will, in fact, get 1. So I'm not going to show all that. But let's look at the thing that's of interest. Find the probability that, so that's what the probability that it has a shelf life, that means time, is 3 years or less. So less than 3 or equal to 3. This is what I'm trying to find in math language. So let's talk a little bit about language over here before we get much farther. We have kind of 2 pairs. More than, you know what that is. That would just be greater than. At most is the same thing as less than or equal to. So these two, one is greater than and the other is less than or equal to. They're called, they exactly cover everything. So you've got the greater than part and the less than or equal to part, and so you have everything. This is true as well, less than and greater than, complements. That's the word we're looking for. They're complements because less than is this part, greater than or equal to is that part, that's everything. Okay, so let's come back here. So we have a shelf life 3 years or less. So 3 years equals or less. So we want to find this. So we're going to look at the probability density function. The probability is just integrating over the range of interest, the function. So 0 to 3, 1 over x plus 1 quantity squared dx. So let's go ahead and work this one out, just for a little bit of practice. First, I look at this and say, is it a basic? No. If it were 1 over x squared, I'd rewrite it in power form, it would be a basic. Is it a lim? Because I see a fraction. So is the derivative of the denominator up here? Well, that derivative of this would be, it's a composite function, so 2x plus 1 to the 1 times the derivative of the inside 1. So 2x, 2 times the quantity x plus 1. That's not up there. So this is not a lim. So that tells me then that this is going to be a power function. So I'm going to rewrite it in power form. It's a composite function. So I look here at the inside, and I see that the derivative is equal to 1. Good news. That means it's easy to integrate. So now I'll have x plus 1. When I integrate, when I do the antiderivative to go up to the original function, then the exponent goes up and divide by. This instruction I have completed. I've done the antiderivative, so it comes over here to be an evaluation bar. Okay, let's rewrite this in a way that's a little easier to work with. This is just minus 1, and that's 1 over x plus 1. That's just a little bit easier to work with. Okay, plugging in 3, negative 1/4. And here, so here again, you need to think about how you want to handle this. You can pull the negative out front altogether or carry it together. I'm going to say I'll carry it together. So minus 1/4 minus, now put in 0, negative 1 over 1, so minus 1. So that's negative 1/4 plus 1, 3/4, or 0.75. So that would be the probability that this one, when I take it off a shelf, has a shelf life of 3 years or less. Okay? Part B says check again and see if it has a shelf life of 3 to 9 years. So how will this change? This will just change one small bit. Right here, from 3 to 9. And then we just complete the entire rest of the process, the antiderivatives, all the same, and this works out to be 0.25. No, I'm sorry, 0.15. 0.15. Okay, and then part C says to do a graph. So the graph of this looks something like this. And so you know, if we're looking from 3 to 9, we're here to here. And if we're from 0 to 3, it goes like that. And actually that shifted over. So when x, so again, let's take a little moment and graph this correctly. When we graph, we want to know the basic shape. 1 over x squared looks like this. I'm only interested in the positive part, so I don't need to concern myself with the negative, just this. This tells me that it shifted to the left by 1. So it's going to be shifted. I might as well find my y-intercept. So when I plug in x equals 0, I get y equals 1. So we have here. And so I don't really need that part. It goes like that. So from 0 to 3, that's the first integral we found. From 3 to 9, that's the next one we found. So again, so probability, we start with a probability density function. We integrate, we find the area to find the actual probability of something happening. Interesting thing, what is the probability that the shelf life, let me just write this way, what's the probability that the shelf life is exactly 3? 3 to 3, it doesn't matter what the probability density function is. If I want exactly 3, I'm going from 3 to 3, and we know that that is 0. Because the probability that you get something exactly 3 when it's a continuous number could be 3.0001, 2.999999. The probability of hitting 3 exactly is so small that we call it 0. Okay, so I think that's everything. So go ahead and work the couple of problems on each of these, and then we'll do that third set, application, which is producer and consumer surplus. That's a fairly easy one. We're going to complete that entirely in class, so that way you'll have no assignments remaining. We'll do that in class. So do the prep assignment for Wednesday, and then we'll do the rest of the material in class on Wednesday, and that way you only have to review for the final going through the weekend. Okay, that's it.